All right, let's get started. I think for the latecomers, Professor Zakor said is out of town today, so I'm a grad student, Vito, and I'll be giving this lecture in her stead just for today. The topic of today's lecture is on realization of IIR filters. So this is part of IIR. You're familiar with IIR filters. I'm sure she's already covered it. IIR filters have this form, h of z equals the summation, k index from 0 to some number q of b sub k, z to the minus k. This is the FIR part, the numerator. And then the IIR part, again, k equals 0, and we have p taps, a sub k, z to the minus k. And this is a general form of an IIR filter. So right now we're talking about realization, but before I wanted to give an overall view of just what this is part of. When you're talking about filter design, there's 3 steps. First is the specification. Someone has to tell you what IIR filter to do. I mean, what the specs are. You know, if you want to make a bandpass filter, say for audio, you want to make sure it's here. All right. Yeah.
How many minutes ago?
Just started. Just started. Okay. You were able to make it.
Yeah, I thought that we had left it as I'll send you email.
I wasn't sure whether it was which email back or forth. No problem.
That's great. Do you want to do it?
No, go ahead.
All right. Okay. There's some stuff that needs to be covered before we do this.
Oh, okay.
So that would be the main reason.
Okay.
All right, sorry about that.
No problem.
All right. I took actually the wrong room. I knew I was jet lagged, but I just wasn't.
Oh, okay.
All right.
Just made it.
Well, I made it last night.
Oh, okay.
There was a possibility I would stay one extra day, but
Okay.
then it
But it
never
didn't-
happened,
it
and I
never
never
was.
sent. I should have sent you an email to clarify, but I didn't.
Okay, no problem.
All right, thanks, Vito.
All right.
All right. Sorry about that, guys. Okay. Let me first make a couple of quick announcements. The graded homeworks are here. And that's homework number 2. So pick them up on your way out. Then there's a homework due on Friday. And that's number 3. And let me assign some homework for next Friday. October 4th would be 6.23, 6.26, 6.27, 6.28, 6.29, and 6.32. Okay. So, and there's also one other thing, and that is the errata for homework solution number 2. It's here. There's a couple of typos in 2 other solutions, so pick them up on your way out. Okay. Are there any questions or comments? Yeah.
I was just looking over the notes from last time, and
You mean the IRCs and FRCs and?
Yeah, we talked about what does it take for LCCD
Mm-hmm.
to LTI. I was, well, I just looked at it briefly, but I couldn't understand why LCCD doesn't guarantee time invariance.
I did it through an example, and what I showed was that you computed the solution to a particular input, and then what we showed is that LCCDE without zero initial condition doesn't correspond to time invariant. So what I showed then is I shifted the input, recomputed the output from scratch, except that I didn't do it real time in class. I wrote on an answer that I asked you to believe by faith, and then that answer wasn't the shifted version of the original answer, and that's how I did. That's how I, through that example, was I showed why it wasn't time invariant. So do you want to? I won't cover this one issue in today's lecture, but one of the reasons I wanted to do today's lecture rather than starting a new topic was to wrap up the end of last time's discussion. But I wasn't going to go this far back that you're asking. Do you want to discuss it at the end of the class? Why don't you bring, if you have your notes, then, yeah, you do have your notes? Okay, then we'll go over it. So, do you follow the argument I just made, though?
I think so. I think I looked at the example and I couldn't prove it to myself. Maybe
You mean the solution, why the solution to the shifted one would be? Yeah, you sort of have to go through all the steps, and I skipped the steps. I wrote down what the answer would have been if you went through all the steps, and then I said, this answer is not the shifted version of the answer we got 5 minutes ago.
well, that makes sense then.
Yeah, I skipped a lot of the steps because I would have had to spend another 45 minutes in the lecture to arrive at that. But so I should have put ... But after you do all of that, the hard work and the labor and, homogeneous solution, particular solution, match the boundary conditions, add them up, all those things, the answer that you get is not the shifted version of what you had before. I realized at the end of last lecture that things got rushed. So I'm planning to go over the end of last time's lecture. One question is, why is the class so decimated? You got subsampled and downsampled and just gone. There's no way. I mean, if I said, hi, in cyberspace, are you watching us live? There's no response. I feel like I'm talking to a vacuum. Did people drop the course? Or they're just watching it from somewhere else? I guess we'll find out on Friday, because that's the day that homework is due. So speaking of that, I have one more announcement to make, and that is that there's going to be a makeup lecture on Monday, September 20th, which is right here from 9:30 to 11. Now, there was a bit of a misannouncement by me saying that the makeup lecture also gets live webcasted. I don't think that happens, but it does get posted on the class website for those of you who couldn't make it to the lecture at that time. Just so that I can have an idea, a quick show of hands, how many people will not be able to make it on Monday? Okay. All right. So there will be on the web, and then also the cassettes for the course are going to be in the next room, so you can also watch it that way. Any other questions or comments? And how is homework number 3 coming along? How many people are done with it? Okay. All right. I know people haven't started it. Oh boy. Okay. All right. So let me get going on continuing the train of thought that we had for LCCDEs and all those other stuff. And so what I'm going to do in today's lecture, talk a little bit about, wrap up the end of last time's lecture, just give a summary of what we concluded, and then also move on into this topic which Vito had started, realization of IIR filters. which really dovetails in a nice way with this difference equation stuff. So let me just remind you what we talked about last time. What we talked about was the following. We started talking about LTI systems being FIR and IIR, and I kept asking you the question is, how do you implement IIR filters if they have infinite impulse response? How do you implement them? How can you convolve an input signal with something that has infinite extent? And the answer was that, well, we divide IIR filters into two classes, the ones that have rational transfer functions and the ones that don't have a rational transfer function. An example of one that doesn't have a rational transfer function is the sink. But with the ones that do have a rational transfer function, that means their system function, h of z, is the ratio of two polynomials, then you can implement them with difference equations. And so implementing or realizing IIR filters through difference equations is the main way of implementing or realizing IIR filters. So then the question came up, well, if I have a difference equations, does it always correspond to a LTI system? And the answer was, well, if you have a linear constant coefficient difference equation, and I explained what all of these things means, by itself it doesn't even correspond to a system. You have to have an initial condition so that a unique input corresponds to a unique output. And furthermore, if you want this system to be linear, then that initial condition has got to be 0. It can't just be some arbitrary number like 5 or 10 or something like that. And then furthermore, if you want it to be time invariant, which is what this fellow here was asking, you have to have the initial condition adjust itself to the characteristic of the input. So for example, if you wanted, if you, let's put back some of the, yeah. So this is some of the pages again from last time's lecture. If you can zoom back here, so this is actually the page that you had a question on. So the question was the last conclusion we came up with was that if you let the initial condition to be equal to 0, then this LCCDE that we have up there corresponds to a linear system. And then we wanted to know whether this thing corresponds to a time invariant sort of a system, and what we did is we shifted the input by n naught, and then we spent a whole lot of time. That's supposed to be ... and I didn't do this one step in class, and you can compute the output due to this input to be that, and we already know the output to this input to be this, and so if I just shift this output by n naught, I get this one, and this answer is not the same as that answer. So that was our proof of why this is not time invariant. On the other hand, if y naught, this initial condition thing, was equal to 0, then it would have been time invariant. So the proposition that we came up with is that for linear constant coefficient difference equation to correspond to an LTI system, you must have 0 initial condition. And then we moved on to sort of causality. If you want to have causality, then you have to have what's called initial rest condition, which means at what point the initial condition is 0 has got to match to the way the input is. So in particular, for example, if the input x of n becomes non-zero at time 5, and I want to have causality, and I have a first order difference equation, and I'll explain what first order means. It means in my difference equations I have y of n's and y of n minus 1s. No y of n minus 2, n minus 3, etc., etc. No more than one delay. That's sort of what first order means. So if I have a first order difference equation for which I only need one initial condition, that initial condition has got to match to the time at which the input becomes non-zero. So if the input becomes non-zero at time 5 and it has all this other junk happening and you want to have causality, then you pick the initial condition at time 4 to be equal to 0. That's the way you make the thing causal. So then we came up with this triangle, and I think this is around the time that I started rushing because I had to catch my flight. And by the way, I did miss my flight, so there was no point in rushing, regardless. But anyway, this is the thing that we came up with last time, which was that if you have an LCCDE, linear constant coefficient difference equations with initial rest condition, it will correspond to a causal LTI system. It also corresponds to h of z, a system function with region of convergence outside of some circle. Okay? So this is sort of like a triangle. Now, some of you came up and said if the region of convergence is outside of some circle, h of n is not necessarily causal, and that is true. So this is a bit, so the causality is a bit stronger than just having region of convergence outside of circle, but outside of some circle. But from here, you can definitely conclude that. And then I talked about the flip side of all of these things, finite rest condition and anti-causal system. It's the same thing, but reversed. So if x of n starts at n naught and is non-zero for smaller values of n than n naught, and it's 0 here, then the final rest condition means that the initial condition has to be chosen just one sample before that for a first order equation, difference equation, or two samples for a second order, etc. So for example, so for example, if x of n is delta of n and the system has to be causal, then you make y of 1 to your initial condition to be equal to 0. So then I ended the lecture by looking at this difference equation once again and saying that this difference equation can have two different realizations. Okay? It can have a causal realization or implementation, and it could have an anti-causal implementation. So here's it's shown better. So if I start with y of n equals a y of n minus 1 plus b delta n, I can assign to y of n a times y of n minus 1 plus x of n. That's the causal implementation. That means the output at time n only depends on the output at time n minus 1 and the input at time n. That is a causal system. However, that same equation, if I can rearrange it. And how do I rearrange it? I bring yn minus 1 to the other side, and I say y of n minus 1 takes this value, and then I rearrange that one more time, replace all the n's with n plus 1. So y of n takes the value of 1 over a y of n plus 1 minus 1 over x of n plus 1. It's the same difference equation as that. Mathematically, it corresponds to the same thing, but it's a different realization of it. In this case, the output at time n depends on the output and input at time n plus 1. So this is the anti-causal realization of the same difference equation. So a given difference equation can have two, in this case it's first order, it can have two different implementation or realization, one causal, one anti-causal. So for this causal one, if the input is delta of n, you have to have initial rest condition, which means y at time minus 1 is equal to 0. For the anti-causal one, you want to have final rest condition, which means y at time 1 is equal to 0. Okay? So this sort of ended up being the last picture in our last lecture, which is I can have linear constant coefficient difference equation either with IRC, initial rest condition, or FRC, final rest condition. In this case, it corresponds to LTI that's causal. In this case, it corresponds to an LTI that's anti-causal. Here, this system will correspond to an H of Z that has regional convergence outside of some circle, and H of Z regional convergence that corresponds inside of some circle. So the same story as we've been talking about is if I just gave you H of Z, it doesn't tell me what my system is. I need to know ROC to know whether it's causal, anti-causal, what it does. The same story is true for difference equations. If I just gave you a difference equation, that difference equation can be implemented two ways, in a causal way or an anti-causal way, if it is first order. And now I'm going to explain this order business, which I keep coming back to. So here's an example of not a first order difference equation, because y of n is a function of, it has y of n minus 1 and y of n minus 2. So this is what's called a second order difference equation, right? And I can come up with three different implementations of it. I can say y of n, I can write y of n as a function of, well, since I ran out of time here, let me now start lecturing here. And so I call it different realizations. It's called realization or sometimes implementation. Implementation is more like whether it's hardware or software, but this is called realization of LCCDEs, linear constant coefficient difference equation. So if I consider a second order difference equation, which is y of n is equal to a times y of n minus 1 plus b times y of n minus 2 plus just x of n. Okay? So this by itself is only a difference equation. It doesn't tell me if it corresponds to any system. It doesn't tell me whether it's causal, anti-causal, or what it does, right? So I claim it's second order, first of all, because it has y of n, n minus 1s, and n minus 2s. And if it had a y of n minus 3 or even x of n minus 3, it would be a third order. Y of n minus 4 or x of n minus 4 would be fourth order. That's the same thing as the order in the differential equations that you're so used to, right? The first order differential equation, the second order, third. What's the definition of a second order differential equation? It has second order derivative. It says d squared x dt squared, right? Just that's old stuff from like calculus and stuff. Anyway, so this thing I can implement it three different ways. Way number one, which is the easiest, is just y of 1 takes a times y of n minus 1 plus b y of n minus 2 plus x of n. And this implementation is what? Causal. This is a causal implementation. And if you were to guess, what would be the region of convergence of impulse response? Outside of something, right? So if h of z has ROC outside. Okay, and then implementation number 2 is the other way around. I get y of n minus 2 is equal to 1 over b y of n minus a over b y of n minus 1 minus 1 over b x of n, and now it takes on I put an arrow here, okay, and now I want to write this side so that it's just y of n. So I add a 2 to all the n indices. So y of n is 1 over b y of n plus 2 minus a over b y of n plus 1 minus 1 over b x of n plus 2. And this is a anti-causal implementation. The output at current sample, the current output sample depends on futuristic input and output samples. So that's, and it's strictly futuristic. Okay, so this is an anti-causal implementation. Okay, and I'll explain in just one more time in a second what the difference between anti-causal and non-causal is. It's just bear with me. And then the third way, so first way is just to write this and get the input from all the other ones. The second way is to write this as a function of the other one. The third way is to write this. You say y of n minus 1 is equal to 1 over a y of n minus b over a y of n minus 2 minus 1 over a x of n. And if I do that, then again I put an arrow here. Then I want to add this here. I get y of n takes on the value 1 over a y of n plus 1 minus b over a y of n minus 1 minus 1 over a x of n plus 1. In this case, the output at time n depends on output both at time n plus 1 and time n minus 1, both future and past. And so is this causal? No. Is it anti-causal? No, it's just non-causal. You can also say it's non-anti-causal, but so this is just non-causal. Okay? So just to explain the difference between, and therefore the region of convergence you would expect to be what? Between two circles. There's going to be some sort of a ring. In this case, the region of convergence of h of c was inside of some circle. Okay? So just to explain the difference between causality, anti-causality, and non-causality, if this is all the systems in the world, I draw a line. This is causal. The subset of them is causal. And then this whole set here is non-causal. Then I can draw another line. Some of the non-causal stuff are anti-causal, but some of them are just neither causal nor anti-causal. They're just non-causal. So anti-causal is a subset of not causal. Non-causal means it's just not causal. It could be anti-causal, or it could just not be anti-causal. Okay? So, yeah.
The only condition for something being anti-causal just means that it only depends on future value.
Exactly.
It doesn't depend on the current or past value.
Correct, exactly.
So a non-causal depends on the past value or the current value.
Non-causal could depend on, let me explain it. So, causal means it depends on present and past values of input. Anti-causal means it depends on present and future. Non-causal means can be anything. Past, future, current, all of the above. Okay? Yeah.
Why do you use the arrows instead of equals?
You could also show equal sign, but I use the arrows because I'm saying this is a different implementation of that same difference equation. The difference equation is the same, but when I write, this is now a system that corresponds to that difference equation. When I use the arrow, I'm talking about the exact system. This, by itself, if I woke you up in the middle of the night and I'll show you that difference equation, so what system does it correspond to? You have to say nothing, because it could be one of three things. There's an ambiguity. But when I put the arrow, I'm just saying that this is the implementation. I'm dealing with that particular realization of that difference equation. Okay? So the same way as a difference equation can have multiple realizations and therefore correspond to different things, different systems, the same the same thing applies to h of z's. The same h of z, depending upon what the region of convergence it has, corresponds to different h of n's. So that's the message that I want you to walk away from. Yeah.
So you also need to specify initial conditions.
Right, and in these cases, yeah, if we wanted these things to be LTI and causal, the initial conditions has to be IRC. And so for this example, because it's a second order, let's talk about case 1. Because this is a second order equation, let me copy it down here. Let's talk about IRC for a second order system. So let's write down case 1 again, which we had here. Which is y of n takes on these values. So if my x of n ends up being something that starts again at time 5, because it's a second order difference equations, I need 2 initial conditions, right? And what would be the proper, what are the values of those initial conditions? They've got to be 0. But at what point in time do they have to be 0? They have got to be 0 at time 4 and at time 3. So the IRC for this case is y at time 3 equals y at time 4 is equal to 0. The 0 has to be there to make it time invariant and linear. And why did I pick 3 and 4 is because my input started at time 5. If I change my mind and give you an input that started at time 10, then the initial condition would have to be at time 8 and at time 9 to be equal to 0. So it's this adaptability of the initial condition with where the input starts that IRC is talking about. So okay. So having said all of these things, one obvious thing to be asking ourselves is this solving these linear constant coefficient difference equations and IRCs and FRCs, solving them using that trial and error method or inductive method or homogeneous plus particular solution thing, that's a really long way. How can we use some of the tools that we've learned to solve them? And the answer is, if they satisfy IRCs and FRCs and all these goodies, you can just use Z-transform to figure out the output of them for a particular input, or even to compute their transfer function. So I'm going to talk about how to solve a LCCDE, linear constant coefficient difference equation, with either IRC or FRC using Z-transform, which is a topic we covered just before this. So suppose I have an again with an example that thing will become clear. So I have an example where y of n minus 5 over 6 y of n minus 1 plus 1 over 6 y of n minus 2 is equal to 1 over 4 to the power of n u of n. And so this is the, in some sense, that's the input. Okay, it doesn't start until time 0. X of n, so it starts somewhere here, and then it does its own thing at time 0. Okay, so what should the initial conditions be? What initial conditions so that we get nice and LTI properties and having causalities? So somebody has told us that this system is causal. Okay, so it's given to us that it's causal. Just the difference equation again doesn't tell you what it is. It could be have a causal implementation, anti-causal, non-causal, any one of those. So we know that it's causal. And how should we pick the initial conditions so that it's LTI and causal? Well, we have to pick initial rest conditions, and this is a second order differential equation. So it has to be at time minus 1 and minus 2. Y at time minus 1 should be equal to y at time minus 2 is equal to 0. That is the initial condition. And now I can, now that I know it's LTI and causal and all these other things, I can, with peace of mind, take the z transform of both sides. I get y of z minus 5 over 6 z inverse y of z. I'm applying the shift property. Plus 1 over 6 z to the minus 2 y of z is equal to, and what's the z transform of that? That's one of the few functions for which we know the z transform almost by heart. It's 1 over 1 minus 4th z inverse. And therefore then y of z, I can rewrite this thing, is equal to, rewrite and then do partial fraction expansion and all kinds of other things. It's 6 over 1 minus 1/2 z inverse plus minus 8, 1 minus 1/3 z inverse plus 3, 1 minus 1/4 z inverse. And now what do I do? How can I compute what y of z is? Well, again, to take the inverse z transform of these things, each one of these guys has two possible inverse z transform, inside of a circle and outside. And which one should I be taking? We have to pick outside of some circle because the system is causal, and we're giving it an input, like a step function, and therefore the output is also going to be a right-handed type sequence. So because of all the givens to us, the fact that the system is causal and input is a right-handed sequence and all that, the ROC that we chosen to compute inverse z transform is outside of some circles. So that means that if I do apply inverse z transform to this, I get y of n is equal to 6. There's two versions of it. Now I picked the right-handed version. 6 times 1/2 to the power of n u of n minus 8 u of n 1/3 to the power of n plus 3 u of n 1/4 to the power of n. So that's the output due to that particular input. And what can I say about the transfer function? Having done that, what can I say about the transfer function of this system? How about the transfer function? In other words, what if the input wasn't this funny-looking step function? What if it was just a delta? So in other words, I had y of n minus 5 over 6 y of n minus 1 plus 1 over 6 y of n minus 2 equals just delta of n. That's our input. What would h of n be? Well, you can take the z transform of this again and compute y of z over x of z, and it's 1 over 1 minus 5 over 6 z inverse plus 1 over 6 z to the minus 2, and then you do partial fraction expansion and do the whole thing, and you get delta of n. But this is called the system function now, h of z. And again, after you factor it out, you will know that the answer here is it's going to have some region of convergence that's outside of some circle. And what that sum is has to do with, after you factor this out and figure out where the poles are, the outer pole tells you what that circle is. Okay. So I think we've managed to establish some sort of a tie or some relationship between like difference equations and rational transfer functions, right? So an important class of IIR filters have rational transfer functions, and we already established that these rational transfer functions correspond to difference equations. And so what I want to just to wrap this up, sorry. So then this h of n is just 6 times 1/2 to the n u of n minus 8 u of n 1/3 to the n. Okay. So this is our h of z, and this is the h of n. And just if I were to plot this h of n, just to convince you that this is an IIR filter, it has 2 u of n's. It starts like that. One of them is exponential decay of 1/2, the other one is 1/3, and you add them up, and this is it. This is our h of n that has infinite extent, and that if we didn't know that you can rewrite it as a difference equation, you would sort of be at a loss how you would convolve with something that has infinite extent. But now that we know we can write it as a difference equation, we can realize these things, right? So from a 50,000 feet view, when you're looking down at this thing, is that you shouldn't despair just because you have an IIR filter. As long as the IIR filter has a rational transfer function, that rational transfer function can be translated into some difference equation, and you can happily implement that difference equation. And I'll talk about that right now, convince you that it's sort of easy to realize difference equations using what? Adders, multipliers, and delays. And adders and multipliers are just computing units you get from anywhere. Delays are just flip-flops. Okay? So what I'm going to talk about now is what Vito had started, which was realizations of IIR filters with rational transfer functions. Okay? So again, a big class of IIR filters, some of them have rational transfer functions, some of them have irrational. Irrational means just not rational. So if I have a rational transfer function, so what we've shown so far or convinced you is that if you have a rational transfer function, then that corresponds to LCCDEs. Great. And so now how do we implement those? Okay? So question is how to realize or implement LCCDs. So I'm going to spend a few pages just to set up the stage for this problem. Okay? And the way I do this is I'm just going to consider h of z's that are rational transfer functions. So it's a ratio of polynomials. Let's write down a general expression for a polynomial. So that'll be the summation k equals 0 to q of b sub k z to the minus k. These are the constant coefficients of the z's. That's a polynomial in z to the minus 1. And then in the denominator, instead of writing a polynomial, I write it in this form. 1 minus summation of k equals 1 p a sub k z to the minus k. I can still write it the same way as the numerator, some k ranging from 0 to p, but I just chose to to make the constant term of this polynomial to be 1, because otherwise there will be a scaling factor that's floating around. This is a polynomial, this is a polynomial, and this is also a polynomial. This is a polynomial of degree q in Z inverse, this is a polynomial of degree p in Z inverse. So this is y of z over x of z, and this is a rational transfer function. Okay? I'm going to assume causality for the rest of today's discussion. Then I can write down y of n in terms of x of n in the following way. So y, and you'll see now why I chose to write these polynomials in this form. It just makes my life easier like 2 minutes from now. So then y of n is the summation from k equals 1 to p of a sub k, y of n minus k. You see why that happens. If I multiply y of z by this thing and I take inverse z transform, the powers of z translate into this. Because you have y of z times a of k times z minus k, and that translates into a of k times a of y of n minus k. It's just a shifting property. Is equal to, and then this gets multiplied by that, and I take the inverse z transform of that, plus summation from k equals 0 to q of b sub k x of n minus k. So that's my difference equation, and that's my rational transfer function. And I'm also going to be, for the rest of this discussion, I'm assuming that h of n is real. If h of n is real, that means a sub k's and b sub k's are also real. Why is it convenient to have real? Because if you have real coefficients, then you do, and if you have a real signal, then all you have to deal with is real numbers by real numbers multiplication, and not a complex number by real number computation. You avoid complex arithmetic if you assume these things are real. And most times people assume that. Now I'm going to come up with flow graph implementations of it, but before I do that, I want to introduce some sort of notations for flow graphs. And we're going to talk about flow graphs both in the context of implemented difference equations in this class, and also in the context of FFTs. Okay, so what's the notation for flow graphs? It's as follows. There's really 3 things I want to do in a flow graph: add, multiply, and delay. And so here we go. If I start with x of n, and I want to multiply it by a constant, get c times x of n, I just denote it by that. So this is multiplication by a constant, c. So that's number 1. Number 2, I want to be able to add 2 signals. And here's how I do it. I have x of n, I have y of n, and I bring them together, put a little circle here, and put 2 arrows. So the notation is if you have 2 arrows coming to a little circle, the signals that those 2 arrows get added, and the output at this circle is just sum of those. So it's x of n plus y of n. Okay? And finally, I can deal with delay. So I have x of n, do z inverse, and I get x of n minus 1. And why do I put z inverse? Because in the z domain, delaying corresponds to multiplying by z inverse. So this is the notation I use in the flow graph language to say that the signal got delayed by 1 unit. If I wanted to delay it by, 5 units, I put z to the minus 5. So that'd be x of n minus 5. Okay, so enough of notation. Having had this notation, now what is the flow graph for a difference equation that we know corresponds to a causal system? So what is the question that I'm going to ask myself is, what is the flow graph for this system, this causal system, which is y of n equals a times y of n minus 1 plus x of n. This is the most studied system in this class so far. So because we know there's a causal implementation of it, that means we're going to say y of n takes on the value a times y of n minus 1 plus x of n. And let's write down the flow graph for it. Okay. Here comes x of n to this node, and out comes y of n. And what this guy is telling you is start with y of n, somehow form a times y of n minus 1. So if some signal is going into here, and if a signal goes to a node and 2 branches come out, that means the value of the signal is replicated here and here. So whatever value we have here is here and here. So if this is y of n, then this is also y of n. So to form y of n minus 1, what do? I put a delay element. And this node now is just y of n minus 1. And then I have to multiply it by a constant, which I call a. So this node here is a times y of n minus 1. And what this realization is telling me is add a times y of n minus 1 to x of n. So let's add them together. 2 arrows coming in, so x of n gets added to a times y of n minus 1. And the answer is y of n. So this point is y of n. So this is y of n and this is y of n. I just connect these two things. So y of n goes to this node, comes out here, comes out this way. And so this is my flow graph implementation, if you will, of this difference equation. Yeah. Could you use the mic, please? Yeah.
There's the circle that you see right over by y of n.
Yeah.
That's not supposed to be a summation, right?
No, because if you have a circle and there's a signal going to it and 2 coming out of it, it acts as a replication. But if I have a circle, 2 arrows are going into it, what comes out of it is the summation. So what I said earlier was, strictly speaking, not precisely true, which is every time you have a circle, there's summation. If there's a thing going into it, then 2 coming out of it, it just acts like a distributor, if you will. Okay? So for those of you who are electrical engineers or mechanical engineers who work with this stuff, you can, like, for those of you who've taken CS150, I bet you can implement this in this FPGA Xilinx stuff. Yeah, you know how you can imagine how you could implement something like this in your 150 class or something. Of course, you can have things that are slightly more complicated than this as well. So now what I'm going to talk about is move away from such a simplistic example like this and talk a little bit more general about different realizations of IIR filters using flow graphs. Okay? So in particular, what I'm going to talk about is 4 different realizations. So methodologies for realizing difference equations, or LCCDEs. And there's 4 of them. One is called direct form 1. The other one is called direct form 2. The third one is not 3 and 4. The third one is cascade. And the fourth one is parallel. So what I mean by that is that if I give you a general rational transfer function like this, there's going to be many different ways of using delays, adders, and multipliers to implement, to realize this. And I'm going to talk about 4 basic categories. Now, what I want to emphasize here is that we're talking about structures for doing that. In general, if I'm designing IIR filters, there's really 3 steps, and what I'm talking about here about realizing LCCDEs is sort of the last of those 3 steps. But what do I mean? So designing an IIR filter has 3 steps in a sense that first you start out with specifications, specs. Somebody has told you, it's usually your boss, so we're building an AM radio, and we want the out-of-band rejection ratio to be this, in-band ripple to be this, transition band just to be this, from this frequency to... It's just a set of specs. And some other system designer who's built an overall system has figured out that if your subblock satisfies those specs, then everything else in this big system will work. So that's God-given or engineer-given or system-given. And then you design the appropriate H of n, the actual IIR filter. In this case, we're assuming rational transfer function. So that means we're assuming that we're designing A sub k's and B sub k's in this H of z thing. What I mean, design the H of z. So somehow, and I haven't talked about this step at all. This is something we'll talk about later in the course. So in some sense, I'm doing things in a slightly reverse way, but as long as I'm acknowledging it, I think you should be okay. So somebody gives you the specs. This is the ripple, the here, transition bands, and you go ahead and using some of the techniques we'll talk about in 4 or 5 weeks, and you design your rational transfer functions. That means the A sub k's and B sub k's in that. And then once you do that, that corresponds to the difference equation. And then you have to what's called realize it. And this is this realization that I'm going to talk about right now. It could be one of these 4 forms. And maybe you can think of a 4th step like implementing. Is once you realize it like this, for example, then you can say, okay, I'm going to use some Xilinx FPGA or somebody else's FPGA to do that. But that step we don't talk about in the class too much. You can realize, for example, this flow graph, besides using hardware, you can realize it by just programming it in C on a computer. We can program it in Java on a cell phone, because cell phones have J2MEs, for example. Or you can, what other way can you implement it? You can implement it on a TI DSP chip. TI DSP chip have these functions galore available to you: delay, add, sum, multiply. Or you could implement it on, I don't know, on an ASIC. You could go to Moses and fabricate and the whole shebang. There's many different ways of implementing any one of these realizations. So I would say step 4 is implementation. So it could be like a C code, it could be FPGA, it could be ASIC, it could be DSP chip, a variety of different things. We again, in this class, we don't talk too much about those implementation issues. But what I'm going to talk about is right now is really step 3, which is the realization. So what do I mean by direct form? Let's start with direct form 1, and let's keep in mind these two. If you can roll up just a little bit, so these 2 pages are in. Thank you. So this is the thing we want to realize. This is the H of z, and this is the difference equation. So let's talk about direct form 1. So how does direct form 1 work? Well, I'm going to rewrite this, even though it chews up more time and space. I'm going to rewrite this so that I can mark it up. Because I'm going to need that intact and clean. This is summation from k equals 1 to p of a sub k y of n minus k, plus summation from k equals 0 to q of b sub k x of n minus k. So I'm going to call this guy a new signal. I call it v of n. And if I do that, then y of n is equal to k from 1 to p of a sub k y of n minus k plus v of n. And let's just expand this for the sake of clarity. And what do we get? We get a sub 1 y of n minus 1 plus a sub 2 y of n minus 2 plus dot 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 plus a sub p y of n minus p, the whole thing plus v of n. So let's realize that. That's not terribly difficult. So how do we go about realizing this? Well, we'll do it in 2 steps. First, I assume the signal here on this line is just V of n. So V of n goes in, and out comes Y of n. This node is a fan-out node. So this is Y of n also coming out. So what I need to do is delayed by 1 multiplied by A1. So I delayed by 1. This is the inverse. At this point now I have Y of n minus 1, right? And then I'll multiply it by A1. Then delayed again. I get Z another delay. If I delay Y of n minus 1 by 1 more delay element, I get Y of n minus 2. That's what I have here. And I want to multiply that by A2. So A2. And I delay it again, and I get Y of n minus 3. So multiply that by A3. I just keep doing that all the way to P times, all the way to that, until this point that I get is Y of n minus P. And then I multiply that by A sub P. And this point was Y of n minus P plus 1. So then I multiply Y of n minus P by A sub P, and I get a new signal. And I add it. This was A of P minus 1. And I add it to Y of n minus P plus 1 by A of P minus 1. And then I keep adding these. And I keep adding this. So now at this point I'm multiplying A sub 3 by Y of n minus 3. But I'm adding it to all the previous one. Adding it to this one. Adding it to this one. So, and then finally this point here corresponds to what? A1 times this plus A2 times this plus A3 times this plus AP times that. It's this whole chain, right? All added up together. And now I have to add it to V of n. So let's do that. Here's an add node. I'm adding V of n to this, to all of these guys, to the sum of all these guys. And if I add these two things together, what do I get? Y of n. So it goes straight to the output Y of n. So this point is Y of n, this is Y of n, and this is Y of n. Okay? So this is not that different from that first order system that we had before. Except that you have to do more multiplications and adds. So now the next step is I have to compute Y of n based on x. And here is the expression for it. Could you roll up, please? Some more. Thank you. Okay. So now I have to compute Y of n. Write down the expression for that. And so how do I do that? Well, to begin with, x of n is coming as an input. And what do I do with that x of n? Well, I can expand this also. This is really like what? It's b of 0 times x of n plus b of 1 times x of n minus 1 plus b of 2 times x of n minus 2 plus b sub q times x of n minus q. That's the expanded version of this sum. So let's just do it. I need to multiply x of n by b naught. So let's just do that. And then I need to delay x by 1 to get x of n minus 1. So this point is just x of n minus 1. And I need to multiply it by b1. And then one more delay. And multiply it by b2. And the last one, this is x of n minus q. I've delayed enough q times to get that and multiplied that by b sub q. And then I have to add these things up. This is a summation node, and I'm adding all these things up. And if I add them all up, that equals what? That's the same as V of n. That's what I had denoted as V of n. So, boom, I just connect. The sum of these two is the same as this signal here, V of n. So that's it. This is the direct form 1 realization of this system or this difference equation. So this is direct form 1. And let's see, how many delays did I need here? How many z inverses did I have? So the number of delays is p plus q. And I can sort of think of this whole system as x of n coming into a blah, which I call h1 of z, and out comes v of n, and then comes out here to another blah, which I call h2 of z, and out comes y of z, y of n. And h of z is sort of the transfer function due to this, and h of 2 is sort of the transfer function due to that. So in other words, h1 of z is just v of z over x of z, and v of z over x of z is what? It's just this blah here, which is just summation. I mean, you can compute it two different ways. You can either say, well, v of n is given by this, and therefore v of z is, you can take z transform on both sides. But you can also look at this. But either way, this expression is given by summation k equals 0 to q of b sub k z to the minus k. Right? So this is h1 of z. And the reason is because v of n is, I'm going to repeat that so that you know it. The reason is exactly this thing here, which is v of n is given by this summation. It's given by summation k equals 0 to q of b sub k x of n minus k. Because v of n is this, that means v of z over x of z is just this whole thing, k equals 0 to q of b sub k z to the minus k. That's the reasoning for that. Okay? So there's a little function here, transfer function here, that relates v to x, and then there's another function, transfer function y of z, h2 of z, that relates y to v. So similarly, h2 of z, this is 2. h2 of z is just y of z over v of z and how do I write that? Well, I can go here, take z transform on both sides of this thing, and what do I get if I do that? You can just say y of z is equal to summation from k equals 1 to p of a sub k z to the minus k y of z plus v of z, and then you can rearrange this da 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 da, and this is sort of as a side issue, and what you get is you compute y of z over I'm sorry, this is v of z. So I'm taking z transform of both sides of this, and I get this, right? And now I can compute y of z over v of z, and I get something like 1 over 1 minus k from 1 equal to p of a sub k z to the minus k. So h1 looks like this, and h2 looks like this. And the overall transfer function, so if I have x of n going to one gigantic h of z coming y of z, then I can just say h is just a product of h1 and h2. It's h1 of z times h2 of z. That's it. And here's h2, here's h1, multiply them together. It's just that expression, k equals 0 to q of b sub k z to the minus k over this one. 1 minus k from 1 to p of a sub k z to the minus k. This is what we got. I'm not saying anything deep. I'm just moving things around and shuffle symbols around, etc. But what I was going to tell you, the reason I did all of these things is that if I look at this picture here, I have a blob which is H1, I have another blob which is H2. The reason I did all of these things is that this thing is H1 and this thing is H2, and in direct form 1 I ended up implementing the numerator H1 first, so this whole thing is H1, and then the denominator of my transfer function H2 next. So in direct form 1 I ended up starting with x of n and then computing numerator, which is H1, followed numerator of H, which is the same as H1, and then followed by denominator of H, which is the same as H2, and out comes Y. That's the way I did direct form 1. And guess what you do to implement direct form 2? What's the... Yeah, I just set the stage for it. Just implement this first, followed by that. So, bingo. So for direct form 2, it's the same as that, but you start with h of n, and you do the denominator. First implement the denominator of h, which is the same as h2, followed by the numerator of h, which is the same as h1. And boom, out comes y of n. Okay? And how would it work? So I start with x, I go to h2, and then I go to h1. And how would the flow graph look like? Just easy. Come back here. Come back here to this page. This was your H1. Let me use a different color. This whole thing was our H1. This whole thing was our H2. Okay? Literally pick this up and put it here, and pick this up and put it there. That's all this is saying. First we did H1, then H2. Now we're going to put H2 here and H1 there. And if we do that, what do we get? Well, we get something like this. Let's keep that here. So you start with x of n going in again, but now I'm going to repeat this H2 blah there. So how do I do that? Boom, arrow, circle, arrow A1, down, Z inverse. I'm sorry, the A1 is not that way. A1 is for this guy. Add Z inverse, multiply by A2, add, da 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 da, all the way. And how did this thing end? One more delay, Z inverse, and then multiply by A sub P, add by A sub P minus 1, add, da 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 da. So here I copied this blah and I put it here. And now I have to copy this blah and put it there. So how do I do that? So this comes here. So let's just copy this here. Circle, circle, B0, go down, Z inverse, multiply by B1, go down, Z inverse, multiply by B2. And these things get added to each other. Okay. Da 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 da, all the way. Multiply by BQ, and then multiply, that's a Z inverse, multiplied by BQ minus 1. These are going down, going up, going down, going up. Okay, so this is it. I just copied this block here, this block there, and this is what I get. So there is Q delay elements here, and there's P delay elements going down that way. And now what can I do to implement the right form 2 in a better way? Well, if you think about it, there's a fictitious signal here, right in the middle, right? That signal goes into this node. This is a node where there's two things coming out of it, going this way and that way. So this signal gets replicated here. Okay? And also there's a fictitious signal coming here, goes down here and there. So the point I'm trying to make is that the signal here is the same as the signal here before the delay, is the same as the signal here before the delay. They're all the same point. Do you agree with that? Because this is a fan-out node, this is a fan-out node. There's no addition, nothing going on, right? So if this signal once gets delayed by this delay, the same signal gets delayed by another delay. Why do I need to have two delays? What I'm doing is I'm having the same signal and delaying it. Why do I have to do it with two different delays? Why can't I combine or merge these two structures, right? It's like this. You're doing a bunch of calculation. You get a number x, and you have to multiply it by some other thing. Why do you need to do it twice? If you do it once, you can recycle that calculation. The same thing here. This signal got delayed twice. I can collapse them. So I can collapse this whole structure with this other structure, but there's a little of a problem. I can't exactly match them. Why? Because this gets delayed p times, this gets delayed q times. So let's just put some explicit numbers for p and q so we can have a real discussion. So suppose that for the sake of completeness, without losing generality, let's just assume that, I don't know, that q is larger than p, without losing any generality. That means here it gets delayed q times, and here only p times. So how many of the delays can I share between the two of them? I'm sorry, let's do it the other way around, because my picture is the other way and I don't want to introduce any typos. Let's just say p is larger than q. Okay, so this guy goes deeper than that guy. This one has 10 delays, this one has 7 delays. So how many delays can I share between the two of them? 7, right? And then there'll be 3 more delays needed for one of the guys, which the other guy doesn't need, right? So the total number of delays that I need in this case is how much? Well, let's not talk about that one now. Let's just collapse them. So suppose p is larger than q, then I can transform this structure here into this. X of n coming in, and okay, now we have the two things combined. Okay, there's B naught going down. This is the joint delay, the Z inverse that's shared between the two of them. Okay, and then from here it goes A1 that way, B1 the other way. It goes A1 this way, B1 that way, and then another delay, Z inverse, and it goes B2 that way, A2 that way. It's like a highway, like an intersection almost. And then dot, and then goes down, dot, 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 dot. But then now I have to plot the rest of this. The rest of it has a change. It goes up this way, goes up this way, goes up that way, goes up this way, goes up that way. And so I keep going down until I assume P is larger than Q. So after Q times, I get to this point after I did Q times. So I'm going to do one last usage of joint delays, if you will. A sub Q and B sub Q. And at this point, I'm done with sharing delays. And now for this side, I have to do more delays because I assume P is larger than Q. So I have to do few more delay, da 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 da, until I reach A sub P. Okay? Like that. And this is like A sub P minus 1, etc. So there's arrows going down this way, arrows going up that way, arrows going up that way, etc. And that's it. Out comes Y of n. So this is called direct form 2. Okay? And it was obtained by collapsing the Z inverses in this. So here what I did is I collapsed the Z inverses. Okay? And now what can we say about this direct 2 thing? What is what the number of delays that's used? Yeah, so number of delays now is max of P comma Q. And in this case, we assume P is larger than Q, so it'll be P. But if it was the other way around, it'll be the other one. And it can be shown, we don't show it in this course, is that for this particular linear time invariant, for this particular linear constant coefficient difference equation, this is the lowest number of delays you could ever use with any structure. This structure looks different than direct form 1. It's going to look different from cascade and parallel and all the other things I'm going to show you later. But this is the bare minimum number of delays you can come up with. Can't go any lower than that. So max of P and Q is the lowest number of delays. So, and that for this system, you can never come on. And it's referred to, when you have the lowest number of delays, it's referred to as canonical form. Okay? And if you want to learn more about that, you can take 221. So to wrap up, we had the same difference equation, the same rational transfer function that corresponded to some IIR filter. And we came up with this realization, which is called direct form 2. And just so that you can remember, this is direct form 1. So direct form 1, we had H1 followed by H2. And to get from direct form 1 to direct form 2, we swap the place of them, and then we collapse the Z inverses, shared them. And this is what comes up, which results in lowest amount of delays. I'm going to stop now, and next time, which is Friday, I'm going to talk about cascade structure, which is yet a different way of implementing that same difference equation and transfer function, etc. Okay? And so make a note that pick up your graded homeworks on your way out, and pick up the 1, 2, and 3. Actually, one more announcement. The course admin, Rosita Alvarez, when I was away, has moved to 195 Corey. So this was done without my knowledge. So graded homeworks that are not picked up, and extra solutions and erratas or whatever the thing is, are going to be with her in 195 M Corey. This is the for people who want errata to. Let me just put one on the other side of the room so that.
So was there a lecture